First, we inserted all of the data points into our calculator lists. Once we had the data inserted, we evaluated the scatter plot and said that a quartic function would be best fit to the scatter plot.
Once we used the quartic regression, we got the function h of t equals 0.0000140311 t to the fourth minus 0.0147912 t cubed plus 4.15083 t squared plus 79.7544 t plus 2475.80. We decided to use 6 significant figures for our rounding because we felt it was the best way to keep the numbers accurate and proportional to one another. We thought that if we went with like 4 decimal places, we weren't going to have enough decimal places in the first leading coefficient, and if we went with like 6, then the last number, the last one that was in the thousands, was going to be a really large number and a lot of decimal places that were unnecessary.
With the first derivative test, we found the local maximum at 331.5 seconds and the local min at 468.3 seconds.
When these values were plugged into the original height function, that gave us a height of 110,718 feet for the local maximum and 101,592 for the local minimum. Now the table has a maximum at 108,942. This happens at 340 seconds. It has a local minimum at 102,522 at 480 seconds. Since both of these numbers are fairly close to our original function, that shows that our function was a good fit for the table data.
To find the points of inflection, we used the second derivative of the altitude function. The point of inflection was at 121.6 and 405.6 seconds. The altitude function is concave up at 0, 121.6 union 405.6, 520, and concave down at 121.6, 405.
The concavity changes at 121.6 seconds because from the video that we watched and the reading in the setup of the problem, we know that the solid rocket boosters separate 2 minutes into flight. This would cause the shuttle to slow down and not accelerate as quickly because before the rocket boosters separate, it has the main engines plus the rocket boosters, and after they separate at 2 minutes, all that's left is the main engines of the shuttle.
At the beginning, there are slight fluctuations in the scatter plot, but after that, it looks like a cubic function. This makes sense because velocity is the derivative of altitude, and altitude is a 4th degree polynomial.
For our equation, we got v of t equals 0.0000528165 t cubed minus 0.019769 t squared plus 11.2065 t minus 51.5758. On the interval 0 to 100, both the main engines and solid rocket boosters are propelling the rocket, which causes the initial acceleration to be very rapid. Then, the shuttle has to cut back the main engines to around 70% power once it reaches the maximum dynamic pressure zone. Then, once cleared of that, the shuttle re-dials up the main engines to 100% thrust as the atmosphere thins and eventually has 0 dynamic pressure.
On the interval 120 to 460, at 120, the solid rocket boosters separate, and all that is left are the 3 main engines. And it is quadratic because they are applying 100% thrust, but as it burns more fuel, there is less weight and more rapid acceleration.
Since the space shuttle can exceed 3 g's of acceleration, it will hold the 3g acceleration on the interval 480 to 500. On the interval 500 to 520, the shuttle goes through MECO, main engine cutoff. This causes the acceleration to drop drastically, and the shuttle runs off only the orbital maneuvering system to achieve full orbit. On the interval 0 to 520, there is not a regression function that really fits the data. But when you limit it to the interval 120 to 460, a quadratic equation really fits the data well. This makes sense because this is the second derivative of a fourth degree polynomial. When we got our equation, we got 0.000171204 t squared minus 0.0424697t plus 12.3591.
From watching some videos, we learned that the shuttle does not go straight up. It goes on an angle. This is what causes the two functions to be completely different. The y2 values are just the vertical rate of change, but the table gives a total velocity taking into account both the vertical and horizontal velocity. Much like the velocity graphs, the acceleration graphs are different because the y3 graph is only looking at the vertical acceleration, whereas the y5 graph takes into account vertical and horizontal acceleration. Are you still there, Mr. Wilson? Thanks for watching our presentation.